Hello viewers, this is Ronald taking you through this tutorial on A-level physics, and in this tutorial we are going to talk about the solutions to UNEB 2019 of paper 1 and particularly question 6. Now where necessary, these constants could be used. So this is the very question I left in the previous video. I believe by now you have already tried it out and ready to check your progress. So let's start with part A, question 6, part A. Part A says, Roman 1, what is meant by a reversible process? And I give it 2 marks. Then Roman 2, distinguish between a saturated vapor and an unsaturated vapor, and they also give it 2 marks. So let's start with question Roman 1. So Roman 1, we can say that a reversible process is the one that takes place in the reversible direction. Note that word, reversible direction, through the same values of pressure, volume, and temperature. So note this word, same values of pressure, volume, and temperature in small changes or in small steps. You can also explain it in this way, that a reversible process is the process that can proceed in a reversible direction by very small changes in conditions, making it take place through exactly the same steps. So it is the wording which differs. You can also say that a reversible process is one which can be made to go to the reverse direction through an infinitesimal change in the conditions causing it. So any of the 3 is okay. Now shall go to Roman 2. Roman 2 says that distinguish between a saturated vapor and unsaturated vapor. So shall say that a saturated vapor is one which is in dynamic equilibrium with its own liquid, while an unsaturated vapor is one which is not in dynamic equilibrium with its own liquid. So basically that's what they wanted in part A. Let's see how marks can be awarded. So if you wrote this first part, that's how you could get the 2 marks. If you wrote this one, that's how you could get the 2 marks. And also if you wrote this is how you could get the 2 marks. So any one of the 3 is okay. Then for this part difference, it is that, and you get yourself your 1 mark. So basically that's what they wanted in part A. Now shall go to A Roman 3. A Roman 3 says, explain why evaporation causes cooling, and I give it 3 marks. So first of all, we shall know that during evaporation, the most energetic molecules escape from the liquid surface. So know that word, most energetic molecules escape from the liquid surface. So the molecules that remain behind do have low kinetic energy. Remember, the ones which are more energetic are the ones with the most kinetic energy. Therefore, when they escape, the ones which remain will be having a low kinetic energy. So since kinetic energy is proportional to the absolute temperature, it implies that the temperature of a liquid decreases with evaporation. And in that case, evaporation causes cooling. So now let's see how marks can be awarded. 1 mark will be for that, another mark will be for low kinetic energy for the molecules which remain. Half a mark will be for you to say that average kinetic energy is proportional to absolute temperature, and lastly is for you to conclude. So basically that's how the 3 marks could come about. Now shall go to question 6 part B. So part B says, describe an experiment to determine the temperature dependence of saturated vapor pressure of water, and they give it 7 marks. So the setup is as shown, so you have to draw this setup as it is. Next is the atmospheric pressure is obtained. So the atmospheric pressure is obtained from this YouTube manometer before you connect it to the vacuum pump. So the tap is opened and the pressure above the liquid is varied to a suitable value using a pump. So you open this tap so that since it is connected to this vacuum pump, you can easily adjust this pressure in this closed limb. It can be either above this atmospheric pressure or below. So in this case, this pressure is this height, this one is the liquid level is below, meaning that the pressure at this point is greater than the pressure at that point. Then the tap is closed and the water is heated until it boils. So after adjusting the pressure, you close the tap and you apply heat to this water. The temperature theta and the difference in material levels H are noted and recorded. So you record the temperature from this thermometer and also measure this difference in material levels H, and also you record it. So in that case, saturated vapor pressure will be equal to H plus or minus small h, and it is calculated. So if this liquid level is lower than this one, it means that the saturated vapor pressure will be capital H plus small h. If this one is above and this one is below, it means that saturated vapor pressure will be capital H minus small h. So that is why we put here plus or minus depending on the level of this pressure in the closed manometer. So the procedure is repeated to obtain the corresponding values of theta and saturated vapor pressure. After that, you plot a graph of saturated vapor pressure against theta. Now this graph shows that P increases with increase in temperature. So basically that's what they wanted in this Roman, because they wanted us to get the temperature dependence on saturated vapor pressure. So this is the temperature dependence. It shows that as pressure or saturated vapor pressure increases, then the temperature also increases. So now let's see how marks can be awarded. One is for you to calculate the atmospheric pressure. Another one is for you to adjust the pressure in the closed limb or the pressure above the liquid. Next is for you to close the tap and also heat until it boils, also needs a mark. Next is for you to measure the temperature and also measure the difference in mercury levels, and also quoting the formula for saturated vapor pressure. Repeating the procedure also takes a mark, and plotting a graph also takes a mark, and concluding the dependence also takes a mark. So basically that is 5 marks, but in the question it was 6-7 marks, meaning that the 2 marks will be on the diagram. So in this diagram, what you do, you mark any 4 well labeled parts. So this and or any 4, as long as they are 4, you mark them, and that will be a total of 2 marks. Now we shall go to part C. Part C says Roman 1, state Dalton's law of partial pressures. And let's first write Roman 1. So Roman 1, Dalton's law states that in a mixture of ideal gases, not that word ideal gases, the total pressure is equal to the sum of the partial pressures due to each gas in the container, provided they don't interact chemically. Know that condition, they don't interact chemically. So now we shall go to Roman 2. Roman 2 says, a sealed container has liquid water, water vapor, and air, all at 27 degrees centigrade. The total pressure inside the container is 69 centimeters of mercury. Then when the temperature is raised to 85 degrees Celsius, the total pressure changes to 96 centimeters of mercury. If the saturation vapor pressure of water at 27 degrees Celsius is 5 centimeters of mercury and the water vapor remains saturated, calculate the saturated vapor pressure of water at 85, and I give it 5 marks. So first of all, you shall see that at 27 degrees Celsius, we have to first convert the degrees Celsius to Kelvin. So 27 plus 273 will give us 300 Kelvin. So what we have done, we have converted from degrees Celsius to Kelvin. Then now next we shall now get the partial pressure at 300 Kelvin. So partial pressure is equal to total pressure minus saturated vapor pressure. So remember, total pressure was 69 centimeters of mercury and saturated vapor pressure was 5 centimeters of mercury. So when you subtract the two, you come up with 64 centimeters of mercury, and that will be the partial pressure at 300 Kelvin. So next is now at 85 degrees Celsius. You have to convert it to Kelvin to come up with 358 Kelvin. And after that, we have to get the partial pressure at that temperature, which will be equal to total pressure, which is minus saturated vapor pressure. So total pressure, we know it as 96 centimeters of mercury, but saturated vapor pressure, we don't know it, and it is the one they want in the question. So shall let it to be PS2. So that we shall quote the formula for ideal gases, that PV over T is equal to constant, therefore P1 V1 over T1 is equal to P2 V2 over T2. Next is to substitute. So where there is P1, I'll put there 64, V1, I don't know it, so I'll first leave it as V. P2, I'll put this, which I've already calculated here, and V2, I don't know it, so I'll first leave it there. T1 is here, and T2 is there, so substitute them there. But we know that the container was sealed. What does that mean? It means that the volume doesn't change, therefore V1 is equal to V2. So that means that this can cancel with this to come up with that. I think we realize that now we have only one unknown, which is PS2. So our aim is to make it the subject. When you cross multiply, we shall come up with that, simplify, come up with that, and make PS2 the subject. You'll come up with 19.6267 centimeters of mercury. So basically that's the saturated vapor pressure which was required. Now let's see how marks can be awarded. So a mark for stating Dalton's law of partial pressure, that is 1 mark. Then converting from degrees Celsius to Kelvin, it is 1 mark, and also getting partial pressure, another mark. Converting to Kelvin is 1 mark, also getting partial pressure for that is also 1 mark. Stating the formula for ideal gas, it is a full mark. Then another full mark for substitution, substituting both pressure, volume, and temperature. Then another full mark for getting the correct magnitude, half a mark, and correct SI unit, another half a mark. So basically that's how you could get the 5 marks. So I believe you have checked your progress and marked yourself. So what I'm going to do, I'm going to leave you with another essay question for you to try out. So that brings us to the end of this lesson. So be reminded that the solutions will be available in the next video. So if you have not yet subscribed, please click the subscribe button below this video so that you can receive updates when the next video with the solutions has been released. Otherwise, thank you for watching, and if you know of any friend or any student who's not yet on this platform, please share this link with them so that they can also benefit from this offer.